Alright, silly people, here's the situation. So on the left here, I have the potential for the delta function potential, and on the right, I have the potential for the finite square well. And we're going to be making approximations on the solutions for the finite square well that shows that the delta function potential is just like the finite square well, but the rectangle is really, really small. I mean, like zero width but infinite height, pretty much. That's what the delta function is. Um, and so the first thing we have to do is we have to make an observation about alpha. Since alpha, uh, Griffiths had a little footnote at the bottom of the page where he defined the delta function potential. It has units of energy times length. Which means if you drew the delta function potential as a really thin rectangle uh, on the position versus energy graph, then effectively alpha is the area of that rectangle, um, which is pretty cool. So we can treat alpha as an energy area. If we were to draw the same sort of rectangle using the finite square well, then the area of that rectangle is just 2a v naught. So we can equate those. We can say alpha is going to be 2a v naught. And that's cool, but we're going to use it to get an expression for v naught, which we are going to plug into this variable z naught, which old Griffiths defined as being a over h bar root 2m v naught, right? So plugging in our definition of v naught in terms of alpha, we have 2m times alpha over 2a, and then those 2's cancel out. I'm actually going to move the a on the outside into the radical, so we have m alpha squared, no, m alpha a squared over a, which is going to give us 1 over h bar square root of m alpha a. Now, a is approximately, well, no, it's exactly twice the width. No. The a is half the width of the rectangle, yeah. And in the limit of the delta function being a really, really small width rectangle, we can let a go to 0, and so our expression for z naught will also go to 0. And a consequence of that is that since z naught is proportional to root v naught, if we're going to let one side of the equation go to 0, we're going to let the other side of the equation go to 0. So this means that v naught is also going to 0, which is what Griffiths was getting on about by saying that the delta function potential is a weak potential, because it will have a really small value of v naught. The next thing that we're going to do is we're going to try and get the expression for the bound state energy in this limit. So remember, in the finite square well, what we did to find the bound state energies, we had to solve this transcendental equation here. Tangent of z is z naught over z all squared minus 1 under a square root, right? And since z is defined as being LA, and we're letting a go to a really, really small number, then for this, we could say that z is small, and so we can Taylor expand tangent of z. Just a reminder, tangent is cosine, or sine over cosine. which in the small angle approximation, sine z will just go to z, and cosine z will go to 1. So this is z, pretty much. I'm going to do an approximation sign there, and set that equal to this thing over here, minus 1. And we're going to do a couple different things to this equation. First of all, we're going to multiply both sides by z. So we're going to be doing z squared equals, and then if you factor the z through into the radical, you just have root z naught squared minus z squared. But then remembering that this is just the definition of kappa A back in Griffiths, we can just say that that's kappa A, and that's pretty useful for us. The other thing that we're going to do to this equation here is we're going to square both sides. So we're going to say that z squared equals z naught over z all squared minus 1. And then we're going to multiply both sides by z squared. So we're going to say z to the 4th equals z naught squared minus z squared. Now, we've already talked about how small z is, which means z to the 4th is really, really small. It's incredibly small. So given that z to the 4th is much, much less than 1, we're just going to approximate it as 0. And so we have that 0 is approximately z naught squared minus z squared. And so we can solve that for z naught squared, and we say that z naught squared is approximately z squared, and we have a value for z squared up here, which means that z naught squared is just equal to kappa A. Right. Now we're actually going to expand the definitions for z naught and kappa. Just looking back, this was our definition for z naught up here. So we're going to say this is 1 over h bar squared. What was it? M alpha A? Yeah. M alpha A. And then on the right hand side, we'll expand the definition of kappa, which is 2me under square root over h bar. And there's an A here. The A's cancel out. This is nice. And then we can use this to get an expression for E. So we're essentially just going to solve this for E now. So it's algebra time. We need M alpha over h bar equals root minus 2me. We're going to square both sides. Now we have, oh my goodness, we have m squared alpha squared over h bar squared equals minus 2me, and then the m's on either side cancel out, and we have that e is just minus m alpha over 2h bar squared, which is the same as the result for the ground state energy, or not the ground state, for the bound state energy for the delta function potential. So by going through the finite square well, we ended up with the same value of E as for the delta function potential, so that's pretty cool. We can do the same thing with the transmission coefficient for the finite square well. So right at the end of this section of the book, Griffiths does give a definition for the, or a result, I guess, of the transmission coefficient for the finite square well, which is looking like this. It's a big ugly expression. but we're going to approximate it down into something that is nicer. So the first approximation that we're going to make is that since the delta function is going off to infinity for the potential, we're going to say that V naught is a lot larger than E. And so we're going to take any place where it's E plus V naught and just truncate it to V naught. So we have 1 plus V naught squared over 4E V naught sine squared 2a over h bar square root 2m v naught, right? So also we have that a is going to 0, right? Because it's a really small width for the delta function, which means that the argument inside the sine squared is very small. So we can Taylor expand the sine squared. So this is another level of approximation that we're doing. The v naught on the bottom there gets canceled out, so this is just 4e down here. And so the Taylor expansion of sine to first order is just the argument. So we have 2a over h bar root 2m v naught all squared. And so actually doing that square root, we get 1 plus, we get v naught over 4e, and then this is going to be 4a squared over h bar squared, and this is 2m v naught. The 4's cancel out, but that's actually not that useful because we're just going to end up regrouping it like this. 1 plus m over 2e h bar squared times 2a v naught squared, right? Moving both of the 2's into the square. But then that's just alpha again. That's the definition of alpha. Or not the definition, what we surmised was alpha. So we can write this as 1 plus m alpha squared over 2e h bar squared. And remember, this is 1 over the transmission coefficient. So we can say now that the transmission coefficient is going to be 1 over 1 plus m alpha squared over 2e h bar squared, which is the same as the transmission coefficient for the delta function potential. So we recovered the result for the delta function potential by treating the finite square well. So that's pretty neat.